Good afternoon, everybody. Today we're going to look at two functions, namely f of x being the square root of x and g of x being the log base 2 of x minus 1. And we're going to look at the composite function f of g of x. We're going to sketch it and then write its domain and range. So first of all, let's go ahead and compute that composite function f of g of x. Reminder, f of g of x means plugging in the entire function g of x, the inside, into f of x. So everywhere that we see an x in the function f of x, we replace the x with all of g of x, right? See, the g of x takes the place of just x. So every x gets replaced with g of x, namely the log base 2 of x minus 1. And so that means that f of g of x, that composite function, becomes the square root of the log base 2 of x minus 1. Now, the log base 2 of x minus 1, right? Let's first sketch g of x by itself. We know that logarithms are only defined when the arguments are positive, strictly positive, right? And so that means that we have restrictions on this function. We already need x to be greater than positive 1, right? And so if I put the positive 1 value here on the x-axis, that serves, x is equal to 1, serves as a vertical asymptote of sorts. And then if you remember what a log base 2 function looks like, there's no stretches or reflections going on. And so from that point on, there's going to be a root at 2, because if we plug in x is equal to 2, right, the log base 2 of 2 minus 1 is log base 2 of 1, right? Here, I'll even do that. If x equals 0, g of 0 is the log base 2 of, sorry, that's not what I meant. Sorry. If x is 2, that's what we were doing. Let's plug that into g of x. If x is 2, then g of 2 is the log base 2 of 2 minus 1, right? Just plugging an x value of 2 in, which is the log base 2 of 1. And what is the log base 2 of 1? That value is 0. Apologies. And so when x is equal to 2, we have a y coordinate of 0, right? So that's on g of x, which I'm coloring in red. So we get a root at 2, 0. And then if you remember what a positive log function looks like, it's going to look like this. It's going to shoot down from negative infinity, and then it's going to grow something like that. Okay, that's roughly g of x. Okay. Now, what if we put a square root on top of all of that? Well, we know that square roots can only be evaluated when the expression underneath the square root is not negative, right? i.e., greater or equal to 0, right? 0 or positive. And so that means that f of g of x, this composite function, is only going to be defined when the stuff underneath the square root, right, the log base 2x minus 1, g of x, is greater or equal to 0, right? That means the y coordinates of that function. That means that we can only start taking the square root of these values when these values are 0 or higher. And so that means that f of g of x is only defined when g of x is 0 or higher, right? And so that means for us that the composite function f of g of x is only going to be defined from here on out. And from there on out, we're just taking the square root of each of the values, right? And so, for example, when x is equal to 3, right? We could plug in another value. When x is equal to 3, g of 3, to get another coordinate point, g of 3 would be the log base 2 of 3 minus 1, which is the log base 2 of 2, which is 1. And so we get another point here at 3, 1, right? 3 and 1. Now, for our composite function f of g of x, if we take the square root, right, the square root of 0 is going to be 0. And then the square root of 1 is 1, right? if you remember your radical functions, between 0 and 1, the square root, right, for x values between 0 and 1, like so, the square root of x is usually bigger than x. And so if you remember what radical functions look like because of the square root, you might notice that between 0 and 1, it's going to hook above the curve, right? And then from there on out, it's going to be a little bit slower to increase in the y values than g of x itself, right? We could plug in another value, a nice value to square root, right? The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. Where would we need to do, if we plugged in x is 17, right? If I make the x coordinate be 17, then g of 17 is the log base 2 of 17 minus 1, which is the log base 2 of 16, which is 4. And so we have a point at 17 and 4. That's, let's say, way out here, right? That's 17 and 4. That would be a nice point to plug into f of g of x because the square root of 4 is 2. And so f of g of x in the black marker is going to be the square root of 4. And so that would be a point around here. Right. That's not the black marker. This is the black marker. So this would be at 17, 2 on f of g of x. And so f of g of x is going to look something like that. It's going to grow very slowly because a log function doesn't grow all that fast. A square root function doesn't grow all that fast. And so the combination of them grows even less fast. And so roughly speaking, this is our composite function f of g of x. And so to write its domain and range, the domain of this composite function f of g of x is going to be the set of x values. It's defined for when x is equal to 2 onwards, right? So we can say x greater than or equal to 2 for any real values of x. And the range of this composite function f of g of x is going to be the set of all y values. The range is going to be 0 onwards, right? That does grow infinitely far up and to the right. And so the y values would be y greater than or equal to 0 for any real value of y. And there we go. That concludes our problem. Again, I hope this is helping you piece some concepts of this course together, right? Remember, logarithm functions are always defined only for positive arguments, right? Square roots are only defined when the expression underneath the square root is not negative, I greater than or equal to 0. And then you can put them together by sketching however you see fit. So I hope this helps, and thanks for watching.